Unit 5A, Lesson 2, Interpret Functions and Applications. Many topics we're going to discuss in this lesson. First, we're going to look at the graphs of different situations and understand what those graphs mean in terms of a context. And then we're going to determine appropriate domains for given situations. And then to end the lesson, we're going to find the average rate of change for different functions that are not linear. Now to the first example of relating graphs to events. The graph shows a jogger's speed during a 20-minute jog around the neighborhood. Along the vertical y-axis, we have the speed in miles per hour. Along the horizontal x-axis, we have the time in minutes. So the first thing we want to analyze or do is describe the jogger's behavior during the 9 to 12-minute interval. So I find the 9 to 12-minute interval along my x-axis. If I go up, I analyze the graph from 9 minutes to 12 minutes, I see we have a constant y value of 6. So that means over the course from 9 minutes to 12 minutes, this jogger was going at a constant rate of 6 miles per hour. They were not increasing that speed or decreasing that speed during that time interval. They were going at that constant rate of 6 miles per hour during the 9 to 12 minute interval. Now to the second part, describe the jogger's behavior during the 16 to 18-minute interval. So we look over from the 16 to the 18-minute interval. We start at a y value of 4, and we end at a y value of 8. So that means over the course of these 2 minutes, the jogger steadily increased their speed from 4 miles per hour to 8 miles per hour. The next topic of this lesson is going to be determining appropriate domains for given situations. You have to recall that the domain is referring to the input values, typically when we have an equation that's referring to our x values. In order to do this, you have to have a solid understanding of the complex number system. You need to understand the difference between rational numbers, integers, whole numbers, and natural numbers. For example, if we were talking about a company that manufactures a certain product, let's say radiators. If we're talking about the number of radiators that company could produce in a single day, say we want to determine what values could represent the number of radiators they could produce in a single day. Well, they're not going to produce a negative number of radiators, so we're not going to have the integers. That includes negative values. We're also not going to include any partial decimals. Either they get the radiator produced or they do not. So we exclude rational numbers as well. So now we have it narrowed down to whole numbers or natural numbers. Well, a company could technically produce 0 radiators in a given day, so our appropriate domain for that situation would be the whole numbers. They could produce 0, 1, 2, 3, 4, 5, and so on radiators in that single day. That would be the appropriate domain for that situation. Now to an example, we want to determine the appropriate domain. A construction company uses the function f of p, where p is the number of people working on a project, to model the amount of money it spends to complete a project. A reasonable domain for this function would be, so we want to choose between positive integers, positive real numbers, integers, or both positive negative real numbers. So we have to go to our input value in this case, which is our variable p, which represents the number of people. We can't have the real numbers or the positive real numbers or both positive and negative real numbers. We can't have real numbers because that would include part of a person. We're not going to have 1/8 of a person working on a project. So we exclude B and D right away. Now we narrow it down to A or C, positive integers or integers. You're also not going to have a negative number of people working on a project. You could have technically 0 people working on a project on a given day, nothing's going to get done, or 1, 2, 3, 4, 5 people working on a project, so on. So the most appropriate domain for this case would be positive integers. In this case, they're excluding that value of 0, where technically you could have 0 people working, because then nothing would get done for that project. So positive integers out of these options would be the best choice. To end this lesson, we're going to work with finding average rates of change for functions that are not linear. It's not a straight line. We can't just identify the slope like we did with our basic y equals mx plus b equations. It's actually using the same idea. We're going to use the slope formula to find the average rate of change, and we're going to go through that right now. So in this problem, we want to find the average rate of change from the second hour, so here, to the 8th hour over here. We can see we have our xy ordered pairs, our xy ordered pair. Now all we have to do is apply the slope formula that we did earlier in the year. M is equal to, M representing the slope, y2 minus y1 over x2 minus x1. We have our x and y value, now we just plug them into the formula and simplify. Plugging in those values, we get 350 minus 110 divided by 8 minus 2. Plugging that in, simplifying, we get 40. And then our label is going to be our y-axis, our vertical axis, represented the distance traveled in miles. The horizontal x-axis represented the time in hours. So this would represent miles per hour. So the average rate of change from the second hour to the 8th hour would be 40 miles per hour. Now to the second example of finding average rates of change, this time not looking at a graph but a table. The table shows the average diameter of the pupil in a person's eye as they grow older. Find the average rate of change of the pupil size from age 30 to age 60. So we're looking at this value and this value. The age is going to be our input, our x value. The diameter size is the output, the y value. So we have an xy ordered pair and an xy ordered pair. Plugging in those xy ordered pairs, we get 3.1 minus 4.3 over 60 minus 30, which is negative 1.2 over 30, which if we plug in, you can simplify to negative 0.04. So the average rate of change from 30 to 60 years old for the diameter of the pupil, it would decrease by 0.04 millimeters per year. So in this lesson, you need to be able to read and interpret a graph or a situation to understand what's going on during certain time intervals. You also need to be able to find the average rates of change from a graph or a table over a certain interval, and then be able to interpret and find appropriate domains given a situation.